Now we're going to take a look at the turning points in the graph and how that number of turning points is related to the degree of the polynomial. So we now have a few different ways that we can identify the degree, right? When the polynomial is in standard form, we can look at the degree as the highest exponent on the highest exponent term, right? When the polynomial is in factored form, like it is here in this first example, right? Then we would add up the degree of each factor, and that would be the degree of the polynomial. So when I look at this first polynomial, x times the quantity x squared minus 4 times the quantity x squared plus 5x plus 6, that x in the front, that first factor, is degree 1. Then we have a quadratic factor, that's degree 2, another quadratic factor, that's another degree 2. And 1 plus 2 plus 2 is 5. So this polynomial has a degree of 5. Okay, now when I look at the number of turning points are marked by extrema that are relative. Remember, relative extrema are where the graph changes from increasing to decreasing, right? Like here, that would be a relative max, or where the graph changes from decreasing to increasing, like this point here, that would be a relative min. So we have one turning point here, this relative max, then another turning point at the relative min. Here's a third turning point, another relative max. Here's a fourth turning point, that's another relative min. So we have 4 turning points in this graph. So the degree is 5, the number of turning points is 4. Okay, when we look at the second example, again, this is factored form, so we add the exponents, the degree of each factor. So 2 plus 2 plus 2 is a degree of 6. Okay, then we're going to count those turning points again. So here's a relative max, here's a relative min, here's a relative max, here's a relative min, here's a relative max. So we have 1, 2, 3, 4, and 5. So 5 turning points, but degree 6 in this second polynomial. Now our third polynomial, this is not factored form, so be careful. Right? We don't want to mistake a polynomial that's not in standard form and just assume that it is in factored form, right? To be factored form, all of these factors have to be multiplied together to create our polynomial. Here, x cubed minus the quantity x minus 1 to the third power, that is not multiplied together. Those are being subtracted. So I would use the strategy from our previous page that we started with, where we're just going to do some mental math to reason through what is the degree of this polynomial. And if I take that binomial and I multiply it times itself 3 times, I'm going to end up with a term of x cubed in the front. Okay, then that's times a negative, so a negative x cubed, and then an x squared and an x and a constant, but I'm going to keep my eye on that x cubed in the front, because now when I subtract an x cubed minus an x cubed, those are going to cancel and leave me with an x squared as my highest exponent term. And I can see that from my graph that I have something that looks like a parabola, right? So, and it's opening up, that means my leading coefficient was positive. So this is a degree 2, right, a quadratic quadratic function, and it has just one turning point here where the graph goes from decreasing to increasing. So degree 2 with one turning point. Okay, now we'll look at this last example here, and we've got factored form because each of these binomials and monomial are being multiplied together. So to find the degree of the whole polynomial, we're going to add the degree of each factor. So 2 plus 2 is 4, plus 3 is 7. So this is a degree 7 polynomial. And then I'm going to count my turning points. So here's a relative min, a relative max, another min, another max. And so I have 1, 2, 3, 4 turning points. Okay, so my degree is 7, my turning points is 4. In the first 3, the degree is always exactly 1 more than the number of turning points. But in this last example here, we see that that pattern does not hold. The degree is not exactly 1 more than the number of turning points, or it would be a 5, and instead we have a 7. So the pattern is not just that it is 1 more, the degree is 1 more, but that it is at least the number of turning points plus 1. So when we write that out, that pattern, we would say the degree is at least 1 more than the number of turning points in the graph. And that brings us to example 4 in the notes, critical thinking about polynomials. In these blanks, in example 4, we're going to use the words always, sometimes, or never in order to make the statement true. So in number 1, polynomials always, sometimes, or never have the same domain. Okay, because polynomials have unbounded domains, we can put anything in we want for x from negative infinity to positive infinity. They always have the same domain, and that domain is all real numbers. Okay, number 2, polynomials always, sometimes, or never have the same range. Okay, that answer is sometimes. Sometimes their range is fully unbounded, as in a linear or a cubic, right? Or a 5th or 7th degree polynomial. Any polynomial that has an odd degree, in fact, is going to have a range that is fully unbounded, the set of all real numbers. Polynomials that have an even degree that is greater or equal to 2, so 2, 4, 6, 8, 10, and so on, they're going to have a half-bounded range. Okay, so that's going to be a sometimes. Number 3, polynomials are always, sometimes, or never continuous. They are always continuous over their domain. Okay, number 4, even degree polynomials always, sometimes, or never have ends pointing in different directions. Okay, that's going to be sometimes, right? Students are tempted to say that this is never the case because our leading coefficient test tells us that when the polynomial is even degree and has a positive leading coefficient, both ends point up. When it's even degree and has a negative leading coefficient, both ends point down. And that is true for polynomials where the degree is even and it's 2 or higher, right? But 0 is an even number, and when the polynomial is a degree 0, that's a constant function, and remember those graph a horizontal line. So the end behavior would be equaling a constant on the left and the right as opposed to both ends pointing up or both ends pointing down. Okay, then number 5, the degree of a polynomial is always, sometimes, or never negative. Okay, the answer to that is never. A polynomial has to have a whole number exponent that is greater or equal to 0. Right, those degrees can never be negative, they can never be decimals or fractions, right? Only whole number exponents that are greater or equal to 0. So that brings us to our secret question for this lesson. We've got 5 more statements here where I'd like you to fill in either always, sometimes, or never to make the statement true. You're going to answer these problems on your own paper and then upload that with your notes to Schoology as the last page.